I'm going to begin the optional examples by redoing example 7, but with an alternative method. I'm going to show a slightly more difficult method than what I showed in class. So I'm going to show the alternative in the hopes that it would be instructive and help you learn how to do related rates. Okay, so we have a conical tank with the vertex pointed down, so it's a cone shape, and it's 18 feet across at the top, which remember is the diameter, and 27 feet tall. It's diameter. And this is the height. And those are constants for both of these. So they're never changing. And it's important when we look at these related rate problems to know what never changes, because those would be items that we won't be differentiating in the same way that we would ones that are varying. So since the whole cone is 18 feet across, that means that the radius at the top is 9 feet across, and that's never changing. The radius, of course, comes from the central line down over, right? And then this height over here is 27 feet. All right, so I've got that piece labeled. Now, the water is flowing into the tank at a rate of 10 cubic feet per minute. And cubic feet is a sign of volume. That's the unit of volume. Lengths are feet, areas are feet squared. So if I wanted the surface area of this cone, that would be feet squared. Volume is cubic feet, feet cubed. So they're telling us that the water is flowing into the tank at a rate of 10 cubic feet per minute. So they're giving us dV dt. And since it's going in, that's why it's a positive value here. If the water was flowing out, it would be a negative value. Oh, and real quickly, I'm doing step 1 right here. Right? I'm making a diagram. I'm figuring out the rates that were given and the rates that are being asked about. All right, now what rate do they want to know about? So they want us to find the rate of change of the depth of the water when the water is 12 feet deep. Okay, so the rate of change of the depth of the water is what we're looking for right there. So they're telling us they want, now the depth of the water is, I'm going to call it variable h. I'm going to call that our depth. So then this is dh dt is given as question mark, right? We don't know what it is, but it's what we're looking for. Now, the only other thing to notice is the 12 feet deep part, but that's not a constant the way 18 and 27 were constant. This is saying, hey, I'm going to fill this up from the bottom of this cone up, 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 and the moment that I want to take a snapshot of is when the water is at 12 feet. So I don't want to use the 12 feet yet. That's the snapshot moment. So we'll substitute this value in later, but it'll be h equals 12 feet. So that's the instant, the moment, the thing that we're going to be considering later on in steps 4 or 5 when we substitute and solve. All right, so step 1 is done. Now we have to consider step 2. We need some kind of formula for all of this. And of course, the formula for volume of a cone is a geometry formula, and it's volume equals 1/3 pi r squared h. Or if you will, it's pi r squared h over 3. Okay, so we can do this and we can use this formula. So I can take the derivative of this right now. That's step 3. So step 3 is to take the derivative of all of this with respect to t. So let me do that. I'm going to take d over dt of that formula. Volume equals, I'm just going to write it pi over 3 r squared h. All right, well the pi over 3 is constant, so that's not really a problem. And then the left side, of course, is just going to be dv dt, so that's easy. So dv dt equals, now over on the right hand side, I'm going to have pi over 3 times, and then these two are multiplied, so I'm going to need the product rule and implicit differentiation to find that. All right, so I start with the product rule. I'm going to take the derivative of r squared. So that would be 2r, leave the h alone, dr dt, right? technically 2r dr dt times h, but I don't like the order of that. So you bring the 2 down, right, using the power rule, dr dt because the variables don't match, that's the back half of the chain rule, and then h is just sitting there because that's the part of the product rule. And then plus, now leave the r squared alone, dh dt. Okay, great. Well, we have some things we can substitute because we're done with step 3. We've actually found the derivative, but we've got some work to do. We know that this value right here is going to be 10, so that's no problem. We know that's pi over 3, no problem. H we know is going to be 12 feet because that was given to us. The dh dt bit right here is what we're looking for, so that's great. But we have some problems because I don't have R values, nor do I have a dr dt value. So I'm going to have to go find those. All right, well, that's when we go back to the drawing board and we work on the side to find R and dr dt when h equals 12 feet. Right? That's what we're trying to do. We're trying to find more values we can substitute. So we're going to have to kind of go do this on over out here on the left-hand side. So the paper's really kind of separated. So we're doing the problem over here on the right, but we're using some the part of piece of paper over here on the left to figure out the pieces that we need. So I'm going to start with looking up at the cone and realizing there's triangles in them that are hills. So I'm going to redraw that piece of the cone. Try to draw my best. And then the water was right here at the moment that we're considering. So we're considering this is H. Let's see, this was 27. This was 9. And then there's water all in here. And then this is R. And we can see there's a relationship here, right? R is to H as 9 is to 27. Or if you will, H is to R as 27 is to 9. Or if you like, H is to 27 as R, H is to 27 as R is to 9. It's similar triangles. So similar triangles, which we learned about in geometry class and also probably algebra 1. So there's a relationship. We can use a proportion. Sets up a proportion. Okay, so we're going to say H is to R, or how about this? H is to 27 as R is to 9. That'll work. Or you could do H is to R as 27 is to 9. It doesn't make any difference, right? So it's a proportion. There are lots of ways to write it. So this proportion is going to help us because we can use that proportion to find dr dt, and we can also use it to find R when H is equal to 12. So that's what we're going to do first. So we're going to use the find R when H is 12. So to do that, I would say, let's see, 12 is to 27 as R is to 9. Multiply both sides by 9. And so I just need to know what 9 times 12 over 27 is. And as it turns out, that would be, let's see, 9 goes into 27 3 times, 12 divided by 3 is 4. So that would be 4 equals R. 4 feet, I should say. Which is great because that gives us our value. So we can say, hey, I can substitute now this value of 4 right here and say, oh, wonderful. That gives me a value I can put in right here and right here. Oops, sorry, that's a little bit off screen. I apologize. So the value here, let me highlight that a little bit better. The value of 4 right there can go right there for R and right there for R. So we're able to put 4 in for both of those R values. All right, great. Now I just need a dr dt. Well, again, I can use this relationship. I'm using this relationship for a lot of things. So I can say, well, if I want a dr dt, I could take the derivative of both sides of this. So let me do this. So h over 27, we're going to find dr dt, sort of. So h over 27 equals r over 9. So I'm going to take d over dt of both sides of this. So that would be 1 over 27 dh dt equals 1 over 9 dr dt, right? Because the 9 and the 27 are denominators, so they're fractions, and they're constants. If I'm going to solve this for dr dt, I just multiply both sides by 9, and 9 goes into 27 3 times. So I find that 1/3 dh dt is equal to dr dt. And I can use that right here and go, okay, well, instead of dr dt, I can put in 1/3 dh dt. Why is that helping? Well, it gets it so that there's only one variable over here, dh dt. There's only one unknown, which is what I'm trying to solve for. All right, so now let's recap. I had this formula. I took the derivative with respect to t. It gave me items that I didn't know. So I went back to my geometry problem. I realized there were similar triangles. And that set up a proportion. I used that proportion to find an r value that was appropriate for h equals 12. Then I also used it to find a derivative. I'm not putting h equals 12 in here because I'm trying to find a derivative, and not of a constant, but of two things that are varying, namely the h, the depth, and the r, the radius. Okay, so now, once I've got this done, it'll be easy, because 10 equals pi over 3 times 2 times so this will be dh dt right here. This will be 1/3 dh dt right here. This will be 4, this will be 12, this will be 4. All right, so that's 10 equals pi over 3 times, and then I just have to multiply all this. So 3 goes into 12 4 times. 4 times 4 is 16. 16 times 3 is 32. So that's 32 dh dt plus 16 dh dt. So 10 is equal to pi over 3, and that's 48 dh dt. Now remember, dh dt is what we're trying to solve for. Right? This is what we're looking for. So I combine them together to make them like terms, and then I'm going to solve for it. Well, here 10 equals 3 goes into 48 16 times, so it's 16 pi dh dt. So that means that dh dt is equal to 10 divided by 16 pi. Now that's an exact answer. It's in feet per minute, because height of the water, depth of the water is only linear, so it's only measured in feet. And then if I wanted to, I could also get an approximation for it with a calculator, and it's about 0.199 feet per minute. So this is exact, this is approximate, which is more appropriate probably for this context, but nevertheless, there they are. And I did step 5 kind of there, actually, here. This is step 4, what I'm doing here. And then solving. And then over here is step 5. And I'm just kind of looking it over and making sure everything makes sense for step 6.